Good morning. My name is Jeff Hollingsworth. I'm from the University of Maryland, and it's my distinct pleasure to be the session chair for what is always one of the real highlights of the SC conference, hearing from the award winners who are the recipients of the Sidney Fernbach and King Kennedy Awards. So today we'll have two wonderful talks. I will start off with the Sidney Fernbach winner, who is Dr. Steve Plimpton from Sandia National Laboratories, Albuquerque, New Mexico Laboratory. Dr. Plimpton's work is in the field of methods and parallel algorithms for a variety of particle-based HPC applications. Along the way, he's contributed a number of algorithms and ideas that have helped with domains such as contact detection and radiation transport. He's best known for his leading work on a large number of open source software packages, which include LAMPS, Sparks, and Sparta. Please join me in welcoming Dr. Plimpton to the stage.
All right, well, thanks, Jeff. I also want to thank the IEEE and this SC conference for this nice award they've given me. But on the first slide, I really want to acknowledge that creating open source software, at least for me, is a highly collaborative effort. So I've tried to squeeze as many of those names on this slide as I could. These are folks both from Sandia and externally. And there's a variety of very good physical scientists, computational scientists, computer scientists, and software ninjas that are on this list. And it's been a great pleasure for me to work with all these folks over the years. I also wanted to thank two of my bosses. Bill Camp was the person who hired me to Sandia almost 30 years ago, became kind of a mentor and a friend. And Bruce Hendrickson was a longtime collaborator, then went into management. And both he and Bill and a series of directors that our Computational Sciences Center have been real visionaries in terms of what HPC can do for Sandia missions as well as DOE missions generally. So they've created a really nice and productive environment where people like myself can work. And lastly, I wanted to acknowledge funding from many parts of DOE supporting these codes and other work over the years. Many offices within the Office of Science, also the NNSA side of DOE, and most recently, the Exascale Computing Program that we heard a lot about yesterday has funded a couple of these codes to prepare for exascale. And I've also listed some industry collaborators for the LAMPS work that we do with molecular dynamics. It's been kind of both exciting and challenging to work with industrial partners because they give you a new perspective on what they expect software to do and the features that are really useful to them. So those have been productive collaborations. So what I want to do to start is give you one slide that's kind of a high-level view of how the great advances in HPC over the decades have impacted particle methods generally, and then give you three short vignettes on the first three codes listed here, which are all particle codes, of how these particular methods on current machines, sort of what length and time scales of problems they can address. So, I think one of the key attributes of lots of particle methods, certainly the ones that I'm going to talk about, but lots of others as well, is that they scale computationally linear in cost with the number of particles. And they also tend to scale very well in a parallel sense. If you add more and more processors, you can often get near perfect N/P scaling as you go to big machines. And that's with the constraint that you still run enough particles per processor to get to that point of scalability. And so that means if over 10 years, if you have a new machine that's, say, 1,000 times faster than the previous one, you can leverage that machine to run 1,000 times more particles, bigger length scale, or even 1,000 times longer time scale, so long as you, again, have large enough N/P, or some combination thereof. So that obviously makes it very possible to run much larger particle simulations. So just to give you one example, and this will probably mostly illustrate how old I am, 30 years ago, when I did molecular dynamics, this was a big simulation for my thesis, for example. About 1,000 atoms, if we could do tens of thousands of time steps on a supercomputer of the day, say a Cray YMP processor, that was a good thing. It seemed really fast. Well, today, here's an example of the scale of simulations I learned about recently. This very large model that folks at Livermore, Vasily Bulatov and his collaborators there and at Germany have run using our code LAMPS. It's one of the biggest simulations I've heard of, at least for our code. It has 2 billion atoms, 500 million time steps, and it runs on the large Sequoia Blue Gene Q machine on about 1/3 of the machine. It took them 2 months to perform this calculation. And so if you wonder why that's possible, it's this linear scaling of the basic method that I talked about. But if you compare the speed of the machines, one Blue Gene core today running LinPack versus one Cray YMP processor 30 years ago is about 40 times faster. So I don't know how many of you remember the YMP. I thought it was really fast back then. That 40 number is amazing to me. And so if you scale that out to a third of the machine on Sequoia, that means it's 21 million times faster than a single Cray YMP processor at running LinPack. If you now translate that into an MD code in terms of atom steps per second, the method from what it used to run on a YMP to what it runs now on a machine like Blue Gene Q gets about 40% of that speed up, 8 million times faster. And so again, this sort of 10 million X over 25, 30 years is something that I think a lot of particle codes and methods have been able to leverage. So it's what HPC has done for particle simulations. Okay, so now let me go to the first vignette, and this is still in the molecular dynamics regime. Classical MD for materials modeling is kind of in between quantum methods and mesoscale methods. The particles, what I'm showing here, represent atoms. They can be coarse-grained blobs as well. The physics is in an interatomic potential that defines the forces between small clusters of atoms. And despite the optimism of the previous slide, the limitation with MD is always how many atoms, how long of time can you run the simulation. So just as a concrete example, even if we had 60 billion atoms, that would only be a cubic micron of a metal. And the time steps are on the order of femtoseconds, so even a billion time steps is only a few microseconds of real time. So instead of talking about a really big simulation, I thought I'd talk about something we're doing in the context of the exascale computing program to make an algorithmic improvement that enables us to get to longer time scales. So this is a method known as local hyperdynamics that Art Voter and collaborators at Los Alamos have pioneered. And Art's the PI of the EXALT project within the ECP program. One of the driving science problems is to look at tungsten surfaces that are in a fusion reactor like ITER that are exposed to helium plasmas. And if you look at the little picture in the bottom right, that's a little simulation of a bubble that's formed from the helium impregnating the surface. And if it bursts, then it degrades the surface and can even affect eventually the performance of the reactor. So this long timescale method is a way to accelerate what's known as rare event dynamics, which is applicable to this kind of problem. It's not applicable to all kinds of MD, but if you have a well-defined energy landscape, say in solids, and groups of atoms that are making conformational transitions to move to a different energy basin, then this kind of method can accelerate it. So let me just give you a pictorial view quickly of how hyperdynamics works. If you think of this as a 1D surface with the black atoms and you have a single red atom, add atom on top of that, it sees this kind of corrugated potential energy surface that it hops around on. What hyperdynamics lets you do is define a bias potential that you apply to a particular pair of atoms, say the add atom and one of its neighbors. And that little inverse parabola, if you choose the height and the width correctly, when you add the blue curve to the red curve, you get a new energy basin which is much shallower, shown in red. And so if for a few time steps the add atom sees that energy landscape, it's much more likely to make a transition to a neighboring basin. So local hyperdynamics prescribes how you choose the pairs of atoms in parallel as well as spatially that you can apply this to every time step. It moves around, is applied to different pairs of atoms, and effectively you can boost the rate at which all the events happen at the same rate. So you get a quantifiable time boost and do a very accelerated form of dynamics, potentially. So here's just a little video. This is a platinum surface where we understand the energy barriers pretty well. 4% random add atoms on top of that. We're running this at 400 degrees Kelvin with a barrier that's underneath those actual, or with a boost that's underneath those actual barriers. And so we get a time boost that's about 4,000x. So that means for this million atom simulation, we can simulate the dynamics for 50 million time steps, and instead of that being a quarter of a microsecond, it's a millisecond of real time. So let me just play the movie here, show you what happens on this surface as we run for a millisecond. The little black add atoms skitter around. The dimers and the trimers are also quite mobile. They start to join up with other larger clusters. And at 100 microseconds here, we're going to run the movie 10x faster to play it out to a millisecond. You see in that histogram, basically all the small clusters disappear and large clusters remain. And atoms are breaking off those. The big clusters are rearranging, but those events happen on a longer time scale. So in that little movie, what we were able to do with the hyperdynamic algorithm was look at 400,000 of these diffusion events as compared to only 100 we would see if we ran that with conventional MD. And that's about a 24-hour run on 4,000 Broadwell cores, so nowhere close to a big exascale machine. But our hope in that project is we can hook this with other methods that work at a higher level to stitch, say, multiple simulations like this together into a very long timescale single trajectory simulation to look at that tungsten helium problem. Okay, the second vignette, this is a Kinetic Monte Carlo method that works at the mesoscale. It's useful for materials processing models of different kinds. I've shown pictures there of grain growth, upper right, diffusion in porous materials, thin film growth, sintering. These are on-lattice models in Monte Carlo lingo, which means the little particles that live on the lattice either diffuse around to other lattice sites or they exchange properties with neighbors. It's a Hamiltonian energy function that describes the local interactions of neighboring lattice points. And depending on how you sample the events, you can do time-accurate simulations or more like energy minimizations with Metropolis Monte Carlo. So I want to show you a little quick movie of a welding model that John and Vina at Sandia have worked on. This is motivated by a NASA materials issue where they take radioactive material and put it inside little metal cans and weld it shut. And they want those to last through long life space missions where the heat that's given off by the decay is converted into electrical power. So welding is really a process of joining two pieces of metal together, and they may have initially a very fine microstructure, like 10 micron sized grains is on the right of that image. And then you run a hot spot, a laser spot, or in this case an arc weld spot across the join between the two materials, and that triggers melting and recrystallization of the microstructure. So those are the colored grains with different orientation that are shown to the left. So let me run the little movie, and you can see as the arc weld passes across it, it induces this very interesting microstructure in the grains that are formed. So this is a few billion lattice sites. It's really a 3D model. You're just looking at the surface. But the reason those interesting grain shapes result is that the arc spot creates this 3D temperature profile with high gradients down into the surface. And the grain growth at any instant in any position is a strong function of that temperature profile. And so the arc basically drags out the shape of the grains as it crosses over them. So that may seem like a funny kind of weld in a join, but the nice thing is it matches experiment very well. These are simulation pictures on the left of the top surface and bottom surface of the metal and micrographs of the same thing in an actual weld. And so you can see the length scales and also the time scales where the spot moves at about 1 centimeter per second are matched very well by this model. The morphologies of the grain structure are the same. And so this enables kind of simulated experiments where we can now modulate different properties of the spot or add impurities to the material that alter the grain growth and see what kind of welds result. Okay, the third vignette is a different Monte Carlo method called direct simulation Monte Carlo. And this is used to model typically low-density gases, look at flow around interesting objects, say in the upper atmosphere. And so a particle here represents as few as maybe 1,000 or 10,000 gas molecules up to 10 to the 9th or 10th, depending on the resolution you need. So the time step is pretty simple. You advect all the particles independently. They may bounce off surfaces or other geometry in the simulation. Then at the end of the time step, you use a grid to co-locate particles and use Monte Carlo rules to perform collisions in chemistry using molecular-based rules within those grid cells. So an example of an adapted grid for flow around the Apollo module is shown there, where the grid is trying to adapt to the density of the flow in different regions. On the left, for a low-density gas, you can do something at the scale of the entire Mir space station and look at flow around that. But what I want to show you are some actual simulations with this method that are done at more continuum kinds of densities, atmospheric densities, where my colleague Michael Gallus has used this method on some large machines to look at very fundamental fluid instabilities and turbulence effects. And he's been trying to show that with a method like DSMC, where you're just modeling things with molecular scale rules at very short ranges, you can actually produce turbulent kind of effects that are normally thought of coming from very long range interactions. So let me show you a little movie of his. This is a 2D system that has about 100 billion particles, but it's easier to visualize in 2D what's happening. The Rickmeyer-Meshkov instability is when you have a light fluid, helium in this case, against a heavier fluid, argon. And when you have a shock that pushes the light fluid into the heavy, you can get these kind of instabilities. So the picture on the right is just a zoom in of the interface where the interesting stuff has happened. You can see these fingers of heavy fluid that remain. Then there's vortices that form at the edges of those. They cascade down to lower and lower level length scales, and those kind of pictures result. So Michael's made careful comparisons of snapshots from those movies with experiments where 2D instabilities were triggered, and 2D Navier-Stokes code doing the same kind of model, again at the same kind of densities. And you can see a very good match between all three. And in fact, at the later times, maybe the stochastic Monte Carlo method is a little better at producing what actually happens in the experiment. So Michael's largest simulations have been 3D turbulence. And these are on a third of the Blue Gene Q machine, the Sequoia machine at Livermore. They take about a month of time. And these are with 1/4 trillion particles, 8 billion grid cells. And because he's running at near atmospheric densities now, physically it's no longer the space station, it's now a cube of gas that's a little less than a millimeter on a side, and he can maybe advance that for 25 tens of microseconds to do these simulations. So that's kind of the limit currently of what, for these kind of methods, the current big machines can perform. Okay, so now I want to take a step back from particle methods and kind of look broader view at the advances we've had in HPC over 30 years, from gigaflops, looking ahead to exaflops, and kind of give you an applications perspective on what that's meant for scientific applications. So I'm going to start that by a quote from this gentleman who was a Pulitzer Prize winning journalist, then an editor, later a professor. And he was commenting on the state of American newspapers. This was actually back in the 60s, before the internet has put more pressure on newspapers. He said, trying to be a first-rate reporter on the average American newspaper is like trying to play Bach's St. Matthew's Passion on a ukulele. So when I read this quote a couple years ago, it kind of crystallized for me some things I was thinking about HPC from the application perspective. So I've adapted this quote for today's talk, and here it is. Trying to do first-rate science on the average petascale, soon exascale machine is like trying to play Bach's St. Matthew's Passion on a million ukuleles. So that probably seems like an odd, even controversial thing to say at this conference of all places, but let me explain what I mean. First, I'll tell you 3 things I'm not trying to say with this analogy. The first is I'm not trying to say HPC is underfunded, like newspapers. In fact, in my memory, this is probably one of the best times to be involved with HPC. There's lots of buzz about exascale, machine learning, even beyond more technologies that are coming around. I'm also not trying to say that the people who make the hardware, the ukuleles, the chip designers, machine architects, are somehow making underpowered or deficient hardware. In fact, I think it's just the opposite. The current and planned hardware is incredibly sophisticated, maybe too sophisticated. And on the next slide, I'll show you that ukuleles actually can be quite amazing musical instruments. And finally, most importantly, I'm not saying that no one is doing first-rate science on petascale machines. Certainly this conference each year with its Gordon Bell winners and talks, other invited talks, are showcasing really creative science that's done on our largest machines. I've also been part of the last couple of years the Insight review process for computer allocation proposals that DOE allocates time on its biggest open machines. And so in my area, I've seen lots of interesting and creative science that's being proposed there as well. So before I tell you what I am trying to say with this analogy, let me introduce you to Jake Shimabukuro. He, many people think, is the best ukulele player in the world. If you Google his name and my favorite song that he plays, a Beatles song, My Guitar Gently Weeps, you'll find a Central Park video that was made of him playing on YouTube. It's about 15 million hits. And I just realized, hearing the audio here, that I can maybe actually play you a few seconds of that. So I'm going to do that. If it works. So this is the YouTube video. And this is about 2/3 of the way through. We get the sound up? So how come it was working when we tried it? Let's stop it here a second. I don't think so. Let's back it up a little second. Okay, and try it again. Sorry. Well, you can see he's playing very fast. For some reason, the audio isn't working when it did a half hour ago. Let me stop that in case it kicks in 30 seconds from now. But I encourage you to go watch that video, not now, please. Sorry, wrong one. Okay. If you watch that, if you're like me, you say, how is it possible that someone can play that fast, that technically proficient, and make beautiful music using only 4 strings? Well, I think the same thing sometimes when I see the heroic calculations that are done by some of you on the largest petascale machines. And the reason for that is I think some of you out here are the Jake Shimabukuros of computational science. Whatever new machine, new hardware you're given, if your application is a decent match to it, you can figure out how to master that hardware, play it well, and make beautiful music, do good science. So that may seem like a good thing, but I'm going to argue it's not optimal. Let's go now back to my analogy. What am I trying to say with this million ukulele idea? Well, again, 3 things. The first is I think we're making machines that are increasingly complex. They're harder to program, they're harder to achieve high performance on, and I'm going to argue they're optimized for a narrower and narrower portion of the field of computational science. The software developers, whether that's at the apps level, the library, or the system level, have to spend a lot of time and energy optimizing for these machines, figuring out how to use them effectively. The next slide, I'm going to argue we suffer from ukulele syndrome. So these 2 realities in the first 2 bullets have a cost on the science. They may be optimal for increasing flops, but I think they're actually suboptimal for the science. All that time, and by translation dollars that's spent, optimizing is not really spent on the science directly. We're leaving a lot of apps and the scientists who use them kind of on the sidelines, and that's frankly because there ain't that many Jake Shimabukuros in this community. So let's talk about ukulele syndrome. If you Google this term, you won't find it. I admit it's fake news. But if you do Google it, you will find a real thing, which is called ukulele acquisition syndrome. So I'm going to take a brief detour into that. Here's a nice definition of ukulele acquisition syndrome. It's that insatiable desire to acquire the next ukulele for your need, to find that perfect ukulele for that favorite sound, song, or moment. So basically, it's people addicted to buying more and more hardware. I mention that because many of us and our organizations have serious cases of hardware acquisition syndrome. And I'm sorry to tell you, the internet says there's no known cure for ukulele or hardware acquisition syndrome. So you'll have to find a 12-step program, maybe the cloud computing people offer that you could join and wean yourself off this addiction. So we're going to talk just about the lesser malady, which is ukulele syndrome. And here's 5 symptoms that you might be experiencing it. I know when I look back over my time in HPC, I think I've experienced all of these at one point or another. So see if you resonate with any of this. When there's a new, faster machine available, do you spend time and dollars rewriting your kernels or code for the nth time to use that platform? Do you end up writing papers for the nth time that show how your code was adapted or how it performs on that hardware? Do you end up using sometimes a brute force algorithm instead of a more clever one because it runs faster or more scalably or at a higher flop rate on the new machine? That's actually an idea that goes back, I think, to David Bailey, the first Fernbach Award winner about 25 years ago. And he had an influential paper about 12 ways to fool the masses when comparing the new distributed memory small computers with these established vector machines. And changing algorithms was one of those 12 ideas. So do you see your code performance decrease on the new machines relative to peak ukulele performance, or PUP? Do you end up running your code on a smaller fraction of the new machine because it either doesn't scale to more nodes, or it could scale if you just ran a much bigger problem, but that doesn't enable you to get to the long time scales that you really want for your science? And finally, do you end up writing allocation proposals for computer time on the machine where you have to jump through hoops to show that you're going to use a large percentage of the machine? And maybe you say you're going to run lots of small, fairly independent jobs in order to get up to those percentages. So on the Insight proposals I review, lots of people propose the latter. It's not against the rules. It's a fine way to do some kinds of science. But I think the fact that a lot of people do that is an indication the biggest machines aren't being used for really big single simulations that they were designed to do. Okay, so what's some reasons that myself or you might be singing the ukulele blues? I want to show some numbers for past, present, and future HPC machines for what are called balance ratios. And I want to thank Cy Hammond, I don't know if he's here at Sandia, who helped me gather this data and understand these numbers. So for each machine, I'm going to show two numbers, a local balance and a remote balance. And the ratios are constructed such that the larger the numbers are, the more imbalanced the ratio is. So local is the number of flops you need to perform in the time it takes to fetch one word, 8 bytes, from local memory on the node in order to keep up the flop rate. The remote balance is the same thing, how many flops you have to perform, but in the time to communicate over the network a word from a remote node. So here are the first three machines going back 30 years, the first gigaflop machine, the first teraflop machine, the first petaflop machine. So these are LinPack numbers for their performance level. And with that as the ratio for flops, the Cray was so fast that you could actually get 2 words from memory and just have to do 1 flop on those 2 words in order to keep the machine busy in a computational sense. At the teraflop and petaflop scale, that jumped up to 5 to 10 flops to pay for 1 local word, and up to as high as close to 200 flops to pay for a remote word. Now I'm going to show you 2 current petascale machines. These each run different architectures at about 20 petaflops. The number of flops you have to do locally now to pay for getting a word of memory is 30, and it's a few hundred to get a remote word from another processor. And last, I'm going to show you 2 planned exascale machines. Obviously, these are kind of estimates, but Cy assures me these are pretty good ballpark numbers. And the details of these machines aren't known, so I'm calling it the to-be-determined door number 1 and door number 2 machine. But now at an exaflop, we've jumped up to 100 or more, a few hundred flops you have to do all the flops you should to keep your machine busy in the time it takes to fetch 1 word of memory. And remotely, it's in the many thousands of flops you now have to do. So if you look at this whole table and just focus on the left side, I think the first thing this community should do is congratulate yourselves. In 30 years, we've gone from gigaflops to exaflops, and an exaflop machine is 1 billion Cray YMP processors. Or I'm sorry, 1 billion gigaflop machines. That's actually multiple Cray YMP processors. Doing that in 30 years is a tremendous accomplishment. But there's had to be some compromises made, and those numbers on the right are one of those compromises. So what do those mean for scientific applications? Well, I think the higher the imbalance ratio is, it means fewer codes in the local sense can achieve single node high performance, and the remote number means fewer codes can scale up to large numbers of nodes. So the bottom line is, by creating this sequence of machines, we're kind of selecting for certain kinds of applications that can withstand those imbalance ratios. And I mean selecting in the evolutionary sense. As we change the landscape of HPC, fewer apps are able to survive on that savanna of HPC for those kind of imbalance ratios. So they get kind of down selected for compute cycles, maybe even for funding, and they get shut out of using these larger and larger machines. So let's take a segue back to particle apps. The 3 particle apps I talked about, and again, I think this is typical of many apps, particle apps. They do lots if you have an expensive model, they do lots of flops per memory access. The interactions are often local, so you don't have to do that much communication for remote information. And if you have zillions of particles, you have natural threading at the zillions level. And so that means, in a sense, I shouldn't be complaining as a person who does particle apps, because again, evolutionarily, we're sort of thinning the herd of apps that can use these latest machines. There's less competition for cycles on that HPC savanna. But even though I tell my continuum friends, you know, the world is made of atoms, that's all you really need, I know in my heart that's not true. Particles don't represent a broad swath of computational science, nor the majority of applications that really need HPC. Many reasons for that, but 2 of them are here. The physics in reality often isn't short range, it's long range, and it's hard to reach long time scales with the explicit time stepping kind of methods that particles typically use. So I wanted to capture sort of the 30 years of HPC and the effect that's had on applications, so I created this little notional graph that's pretty qualitative. Across the timeline there on the y-axis, what I'm showing is the percentage of different kinds of applications that can effectively use these different paradigms. So we've gone from a shift, maybe vector machines started to get popular in the mid-70s. There was about 15 years where they dominated. then a paradigm shift, distributed memory MPI. We had a pretty good run there, about 20 years. 10 or so years ago, the era of GPUs and accelerators like the Xeon Phi came in. Applications had to adapt to that. And now looking ahead to exascale, we're talking about other kinds of paradigm shifts that will require reconstructing our applications. So these curves, the peaks, are kind of drawn in a way that I'll talk about here. Probably those curves should somewhat overlap. In the case of vector going to distributed memory MPI, the vector machines actually went away pretty quickly. So if your app didn't run under MPI, it couldn't use the cycles of the new machines. But over 20 years, lots of codes could adapt, and so we probably reached about the same peak we did with vectorized applications. I think the last 10 years on GPU and Phi, there haven't been near as many applications that have adapted to that and been able to use the largest machines at scale that have those accelerator chips in them. So I think you'd agree that the peaks would be much lower if I was only showing not just apps that had GPU-ized or Xeon Phi-ized their kernels, but if we showed the ones that actually scale to large machines, it would be relatively few applications that can run on thousands or tens of thousands of GPU today. So that purple curve has not yet reached those original heights. I think there are folks, maybe in this room, with quantitative data on this. The big supercomputer centers, especially those that deploy multiple machines, could tell us the statistics for what their users are choosing to run on. The big labs like Sandia with a wide variety of apps, I don't have hard numbers, but I know just anecdotally, even 10 years into the GPU revolution, there's only a small fraction of our apps that are really ready for GPU, especially that can run scalably on large numbers. And that's because the apps are very complex. It's a lot of effort and time to do that conversion of the kernels, and some of the physics, frankly, doesn't map really well to a really fine-grained style of parallelism. So what does this have as an impact on science, if I summarize this? Well, I think it's two things. There's an opportunity cost in an economic sense for continually having to adapt our apps to new machines. It doesn't really, that work in and of itself doesn't advance the models, the numerical methods, the algorithms, and it doesn't directly impact the science, only indirectly once the code is ready for the new machine. And I think deploying computers that are hard to use and code for has many effects. I've already argued it shrinks the number of applications that can use it. I think it leads to less multi-physics, less multi-scale, because that means you have to have two algorithms or two apps that work together both well on that new architecture. And maybe most importantly, I think it shrinks the pool of people that can effectively program for these machines. In my experience, there's lots of casual HPC users that are not the Jake Shimabukuros of the world, but they're often better physical scientists. And so if we make them team up with a handful of Jake Shimabukuros and make the machines hard for them to use and code for themselves, I think we're losing some of their science contributions. So I want to close just by showing you 3 quick slides of 3 other fields of physical science that have endured or gone, I shouldn't say endured, but have embraced rapid technological change over the last 30 years or so and how they've adapted to it. The first is modern cell biology. I've just listed 4 technologies here that have kind of revolutionized cell biology. A lot of them have to do with DNA, either replicating it or sequencing it, or with the case of CRISPR, now they can do genome editing in live cells. And the thing about all these technologies is once they became established, they rapidly became ubiquitous in the field. Any lab, any grad student can learn these techniques and use them himself. So that means if a PI is going to write an NIH proposal, they don't need to team with experts from other fields like CRISPR. They can do the work themselves within their lab and exploit their creative ideas. So how would it be in HPC if we could achieve that level of ease of use? If any grad student, any lab could use productively the newest machines that we deploy. So the second field are physical sciences that deploy billion-dollar instruments. I just listed 3 of those I was a little familiar with. The Hubble telescope, which was talked about in the keynote talk a little bit. The spallation neutron source at Oak Ridge that provides high neutron fluxes for materials interrogation. And the Z machine at Sandia, which produces very high electromagnetic fluxes to impact materials. So these cater to lots of users. The numbers are there for 10s and 20s of years that these facilities have been open, and they do frequent upgrades to increase the capability of their machines. But I think all that, they solicit user proposals, Hubble, even from amateur astronomers can get time on Hubble. But all these facilities, I think, do a very good job of shielding the complexity of the billion-dollar instrument from their users. They just bring their samples to Z or the spallation neutron source. They see the fluxes. They don't worry about what happens behind the scenes to produce that. So what if every time we deployed, say, a 20 times faster HP machine, all the people who had used the previous ones didn't see any of the new complexity? They could just bring their codes to the new one and see that 20x speed up. Wouldn't that be an enabling thing for scientific computing? Okay, so the last analogy is with high-energy particle physics. Places like CERN and Fermilab, these are not pictures of the accelerator. Those take square miles of geography. These are pictures just of the detectors that have to be built every time one of those new accelerators goes online or there's an upgrade to a new energy regime. And those are hundreds of millions of dollar devices. They involve hundreds of people, years of effort to make those detectors, and they have to exist for the new machine to be useful. And then the machine performs a handful of experiments that are highly impactful. These are looking at origin of the universe kinds of questions. But I think even physicists would agree these are experiments in a fairly narrow subfield of physics. So I ask you to think about, is HPC more like cell biology, where everybody, grad students, any lab can use it? Is it more like the user facilities, where we're shielded at the application level from all the complexity of the new machines? Or is it more like high-energy particle physics, where there has to be very large investments of time, people, and money in order to get things ready to use the new machine, like the detectors that they build? So with that, I'm to my last slide. I've tried to make these couple of points here. I'm hoping we won't just build hard-to-use machines that require heroic ukulele players like Jake Shimabukuro to model a handful of good science problems. I hope we can move beyond that to actually create easy-to-use machines and software that enable huge numbers of sort of mere mortal computational scientists, the rest of us, the 99%, if you will, across many fields of science to do amazing things. And I hope you don't see my remarks as criticism of this community. I'm actually part of it. I hope rather you see it as inducements, wherever you fit in the HPC ecosystem, that you can try to do the things you do in a way that insulates the users, the scientists, if you will, from the growing complexity of our machines. And that you can do your part to make life easier for the apps and the science. I think one metric of when we're successful doing that is when a tool we create, whether it's a piece of software or it's an actual machine, when that tool is so powerful and has done its job, is when users, like the scientists, don't need our help in order to use it effectively. And they can do things with it that we didn't even imagine when we created the tool. And so with that, I'll leave you with a quote from a software engineering expert, David Parnas, that I find motivational when I write software. I think it applies to hardware as well. He said, "Complexity is not a goal. I don't want to be remembered as an engineer of complex systems." And with that, I'll stop. Thanks for your attention.
Thank you. We have time for a few questions. I believe there's some microphones out there. I'm looking to see. Yes, I see the microphones. If you could come up to one of the numbered microphones and ask a question. While people are coming to the microphones, I will ask you one question. So what was very impressive about your work is the wide range of both time and spatial scales and the diverse application domains your tools have been applied to. What do you think the success factors were that allowed you to have your libraries so widely used on such diverse domains?
So really the three vignettes I gave were for three very different kinds of particle models. So I would say the basic thing about the length and time scales is just the way the model itself is constructed, whether it's our codes or other codes that do the same thing. In the case of DSMC, for example, it's just very naturally because of how many particles or how many physical molecules the particles represent that you can get to a variety of length and time scales. So maybe the value added that we've tried to include is the ability to run these at scale on large parallel machines, and then that gives you another boost in the length and time scales you can get to.
Great, thanks. Does anybody have any questions? I don't.
No ukulele players in the audience?
Yes. Any questions coming up?
Okay, I hope I haven't offended anybody in the
Well, I had one more question for you. Well, we'll see if anybody else wants to come. So, do you think the modern next generation exascale machines, what can we be doing now so that we can have more people use these machines and effectively use them?
So I thought a little about that. I didn't really think I'd have time to cover new ideas. I was actually hoping people that come to this conference would have probably better ideas than I do. I think we might be tempted to say, you know, the interface with the actual users, the scientists, is the application. So it's all on the people who write the applications to enable this ease of use. But I think, and I hope I gave you some evidence, that I don't think that's the optimal way to do it. Because then you have to find the 1% Jake Shimabukuros to support the 99% the rest of us. And I just don't think that scales. It needs help across the spectrum of HPC. And besides today, having this 1%, 99% discussion isn't a very politically correct thing to do. So that's not a good idea politically.
Back here at mic 3.
Yeah, we've got someone at, looks like mic 2 and 3. So why don't we start with 2 and then we'll go over to 3.
So as a computer scientist and a musician, I resonate a bit with what you talked about here today. Both sides are equally guilty of shiny object syndrome and buying the next toy. But the problems that you discussed, how much of that would you say is due to a lack of investment in HPC re-architecture versus the algorithms that we run on them?
So I don't think HPC has lacked for investment, certainly in the big picture of all the things the government, for example, invests in. I think there's some, I didn't talk about, there's some very fundamental physical challenges in continuing to increase flop rates. I mean, the whole issue with Moore's Law and the sort of running out of Moore's Law, at least at the individual core level, those are fundamental pressures that have forced architecture choices and designs that are part of those imbalance ratios that I talked about. I guess what's maybe been too much of a driving force to me is chasing the elusive flops, trying to climb up that 500 list and just produce faster and faster machines, and those really aren't the right metrics for making the machines easy to use and easy to do science on. So that's maybe where the field as a whole has gone off in a direction that isn't most productive for science.
Great. Why don't we jump over to mic 3?
Thanks. So this is a kind of an off-the-wall question, but since your field encompasses lots of Monte Carlo, I thought it might be an appropriate one. Are random numbers a solved problem today?
Are random numbers?
Yeah. Is there anything more we should try to discover or improve in the technology of generating random numbers for simulations of the kind you do?
Yeah. So that's a good question. I think it was, if I remember, John von Neumann that said anybody that uses a computer to generate random numbers is in a state of sin. So I think one pressure on the quality of random numbers generators has been the high level of parallelism that today's machines exploit, but that's motivated a lot of nice algorithmic and development work of random number libraries, especially ones that can scale up to sort of millions of independent streams. So I wouldn't say it's the biggest challenge in these codes. I would say it's a reasonably solved problem, but there's probably always advances to make, especially as we go to exascale.
I think we have another person back at mic 2.
Hi, and I cannot agree more for your advocacy for make those facilities more easy for users to use. But I think right now the situation that we only measure the flops, we don't actually measure how many hours those graduate students or faculty members are spending on those machines. I think the root cause is the measurement is wrong. So that's actually my comment. Thank you.
Yeah, I think I would agree with that. Thank you.
Hi. This was a very nice talk. I have looked at productivity for a long time. So I wanted your opinion on what makes experts work. Because if the rest of us can't be like them, are we being stupid, or are we expecting life to be very easy, or are the experts getting it right, and do they have the drive to use these new machines?
Well, I've certainly met at Sandia and elsewhere a few of these Jake Shimabukuros, and I don't think I could quantify exactly what makes them tick or what makes them so productive. I do think big projects, big teams like the Exascale Computing Project, for example, is trying to put together, does increase the chances that average people like myself can rub shoulders with some of these real software ninjas, the Jake Shimabukuros, and maybe learn some of their tricks, but at least integrate their ideas and their techniques into our codes more easily. So that's a good aspect of these high-level collaborations that are sort of required. If you find the answer to your question, let us know. What makes an expert?
All right. With that inspirational goal, join me in thanking Steve one more time for his presentation today. The second talk of this session is for the Ken Kennedy Award winner. This year's Ken Kennedy Award winner is Jesus Labarta. Dr. Labarta is a professor of computer architecture at the Technical University of Cantalona, and also has worked in a vast number of fields of parallel computation, ranging from computer architecture to memory systems to programming models, parallelizing compilers, and near and dear to my heart, performance analysis, measurement, and performance prediction. In addition to his academic roles, he also is in charge of the Computer Science Research Department of the Barcelona Supercomputing Center. And if that doesn't keep him busy enough, he is also in charge of the, let me get this exactly right, the Programming Models and Resource Management Activities sub-project of the Human Brain Project. Please join me in welcoming Dr. Labarta.
Okay, morning. I'll try to spend the next 40 minutes or so talking about this title, which my daughter asked me whether it was mine or not, because looks like very, I don't know, philosophical or transcendental, or I'll try to make a presentation of philosophies about points that I think have to do quite a bit with what has been mentioned before by Steve. Maybe you can go through them and think whether you agree or disagree, or these are directions that are of interest to follow. I will nevertheless start by, if this moves, which doesn't. It was supposed. Now it does. I want to extend a little bit what Jeff said about me. And I think it's essentially this. I grew up in a department which, as he said, was a computer architecture department, where the important things were, I don't know, interconnects, vector functional units, caches, these kind of things. And then jumped out of that into a different world. And I want to kind of recognize and acknowledge my respect for Ken Kennedy, because at those times, well, some time ago, once upon a time, yeah, I was doing, what you would expect from the architecture department, which was hardware. And, well, probably was not enough. Is not enough. I mean, we made this machine, we made it to do a matrix multiply, and we jumped to the other side, to the side of software. You needed something else. And when you switch between two states, typically you have a potential barrier that maybe something like a catalyst can help reduce and can help you go over it. And actually, this is what happened with me with our group, with Parascope, with the work from Ken Kennedy on a compiler. We had a project here cooperating with Convex, and we used Ken Kennedy's infrastructure to actually do translation from sequential Fortran programs to HPF. I didn't have a personal contact with Ken, but I got the support and we were helped by him and his team and having these tools available. And I think this is something that for me was very important. So having said so, I will just during the presentation focus on the type of things that I think I've learned since then. What worries me, you may agree, I will present my personal visions of some of these things. You may agree, disagree, but well, we can discuss about that later. But I will start by presenting a vision of what has happened with the architecture in the last years, and why I think we are living in this revolution that we were mentioning. And probably the vision is, you know, once upon a time, life was easy because we had this ISA level, which decoupled what applications were implementing on top of something which is what the architects were doing. And that made life relatively easy. It also, this is a big problem, but it also happened, it actually happened that multicores broke that layer, that decoupling, and we now need to be very much aware of what's underneath that layer in order to exploit it and in order to get real performance out of those machines. And this is a complex, what makes actually machines complicated and makes complicated the use of those machines. So this is actually the impact of that is applications grow in size and complexity. And then the second thing I want to comment is what happens with this increasing complexity and also the variability in our systems that we are facing now. And this generates a divergence between our mental models, how we think machines behave, and the way they really behave. And the problem is that because we target, when we program, we target our mental models, we write the models, the programs to our mental models. This divergence is actually causing, I think, a lot of difficulties. So in this context, what I think is what programmers need, and I would summarize in one word, is I think there is a need to give hope to programmers. And I think it matches a little bit with what you ask, in the sense that we have to offer the mechanisms to use machines, whatever they are, whatever they have inside. Okay? So this is kind of the context where I think two technologies are key and very important for that. First, programming models to allow us, again, to decouple the programmer from the system and have these productive type of environments that we think we need. Second, we need to know how machines behave. We need to know what's underneath of these systems. So these two technologies, programming models and performance analysis tools, are two very important components of the research that I think has driven and has steered the work that we've been doing for the last years. And this is what I would like to talk a little bit about. So I will focus on starting on the programming models part, and I will just try to repeat again the type of situation that I feel we have with this as a result of what I commented before, is that if we have an application, a problem, something we have to solve, we develop initial codes, but these codes have long life cycles, and through these life cycles, with more or less effort, we start increasing and increasing their size. We start putting platform specificities in them, we start putting optimizations that target one system, but if you think of them in the long term, they may not be good for the future. We start putting a lot of hardwired, scheduled decisions in our source code. And I think that the slope, well, sometimes we even go further and we go to totally different kind of structures of the applications. And this slope, I think, is kind of dangerous. I would like to show, and I think we should demonstrate, we should get to a situation where there is actual hope for programmers in that it's possible to evolve to a version of the codes which are simpler, cleaner, and still performant and still portable, both on not only functionality, but also on performance. And what is the type of directions or approach that would take us in that direction? I think we have to recover what we have lost. We have lost this decoupling between architecture and the programmer, and the vision, the idea is we have to recover that. Probably we cannot do it now at the low level of the hardware itself. We have to go to a little bit, or let's say to a higher level, but they still have an interface which decouples the applications on top of it from the underlying infrastructure. I think it's extremely important what this interface is in a way that conveys information that the programmer may have to the infrastructure, but does not specify really a lot of how to do things especially. What we need then is runtimes that are able to map the user requirements to the underlying physical machines, that if the machine changes, you adapt the runtime, and then the important thing is that the application still remains. And this was the approach of what we have been doing with the STARS programming model. The idea is this interface, this layer on top, is just a standard sequential program, okay? And we kind of parallelize the execution of that program in the same way that architects have been parallelizing the execution of ISAs for a long time by using superscalar processors. We can actually reuse the techniques from the superscalar or from classical architecture techniques, let's say. We can reuse them at the cursor level and achieve the efficiency and the coupling between applications and systems. So this is the work that we did with the STARS kind of family of programming models. The idea is you still have single sequential program. You specify tasks in that program. We cannot do what the architects did, that they had a manual where they had an ISA, and this is the instruction, and this reads this register and writes the other one. Now the programmer has to specify that. It's on a single address space. And the directionality, so you define the task and you define directionality annotations, what are the inputs and what are the outputs. It's just replicating ISAs at a higher level. And replicating the technologies the architects have been doing, one can get parallel execution essentially for free. This is the nice way to put it, the idea, and this is what we have been trying with the OMS programming model, for example, which is a result of an evolution of different efforts, but where I want to just show is some of the fundamental characteristics. And I think one of the very important characteristics is that you have a single interface, a single pragma, the directionality annotations that lets you specify not only information which is needed for the runtime to detect potential concurrency, but also information that the runtime can use to manage locality. We believe that this is a proper interface that actually allows you to convey sufficient information to the runtime for the runtime to make intelligent decisions, and still does not force the programmer to be specifying and controlling everything. So you have these pragmas where you specify what are the inputs, what are the outputs. From the execution of the program, a task graph is dynamically built, and this task graph actually execute and can execute out of order as long as you honor the dependencies. And you can execute many times, and you can have many different execution orders, but all of them are valid. It's important to have tools also to understand to really understand the detail of the internal behavior. So this is what we have tried to do, this development of these models and still having those tools that let you get a feeling of the internals, of the insights, of the details. And we have tried to do, this is kind of the strategy, is kind of to run parallel to OpenMP and being kind of a forerunner. The analogy I like to use is kind of this cycling thing where there's a guy who, when they go uphill, there's one guy who goes in front and actually looks and kind of pulls from the others. There's like a rubber band that pulls from the other guys and helps them go faster. This is what we would like. There are risks here. If you pull too fast or you pull too much, the rubber band breaks and then you disconnect and then you're lost. You have lost probably your team leader. So this is the type of strategy, the type of activity that we have been trying to do. We have been contributing some of the ideas that we demonstrated in the OMS infrastructure into the OpenMP. This is what we would like to continue doing. We are taking, well, now we're releasing an OMS 2 version with some features that it's always like all the strategies. You play a game, you sometimes manage to really pull this rubber band, sometimes it breaks or not. We're trying to experiment with new things that we hope will be useful for the future. And I would like to mention some of these things. So one of them is the support for regions, which we have actually proposed in long time ago. But I think this is something that is important. If you look at syntactically in OpenMP today, still, syntactically you have the support. You can specify subarrays in a dependence. What the implementations don't do is really to take into account exactly the subarray in order to compute exactly the dependence. They use essentially just a sentinel representative, the first element of that subarray. What we think is that it would be important to really have a full proper computation of dependencies. This would be a huge flexibility. And the example I like to use is the Gauss-Seidel type of thing. Gauss-Seidel, where you compute for every point, you have to take, you use the previous computation, you could use a computation that you obtain a little bit before, and you could use some data that you had from the previous iterations. So, the actual way to run this in parallel is to really go on a wavefront type of approach. The problem with the wavefront type of approach is that you have to modify the original source code. Typically, the source code going by rows and columns, and 2D nested loops are very simple codes. If you start tilting the iteration space, or you start, the code gets a little bit complicated. And the nice thing is, if you keep the original source code with the original 2D loops, but for each of the iterations inside it, you specify what are the inputs, left, up, right, and down, the runtime is able to automatically itself, if it can compute these dependencies properly, it's able to automatically give you the wavefront. And not only the wavefront, the fact is that as long as this wavefront proceeds, you have, again, if you have several iterations of this Gauss-Seidel, you can actually start different wavefronts as long as you keep a separation space between them. So there is a huge opportunity for more concurrency. There's a huge opportunity even for locality. If you start new wavefronts of later iterations, you are actually accessing data more in a more local way in the temporal sense. So this is a thing that we would like to push for. The next thing that we would like to push is nesting. I think when you look at generating parallelism for millions or tens of millions of cores, I believe that the current bottom-up approaches are not appropriate, not good. We need to try to leverage, get some parallelism from everywhere we can. Every level contributes. And the idea is that you can instantiate a graph with these coarse-grained nodes, but internally each of those can be constituted of independent tasks. As of today, this model in OpenMP, each of these tasks, nested is supported, but each of these tasks is kind of a container. Inside it, there are new tasks, but until you don't execute a given task, and for example, the task at the bottom cannot execute until the other ones have finished, then what we end up having is that these boundaries between the outer levels are kind of very restrictive. We would like to try things like, even if you instantiate in this way, what if you are able to just explode one of these bubbles, reorganize the graph dynamically, okay? And actually, you say, well, this is not giving me more parallelism, but this is giving me one thing, is I can do all of that, which is otherwise it's work instantiation I would have to do in the critical path. I can do all of that with much more anticipation. So it lets me overlap a lot of the overheads with other computations. I can do the same thing of just in other parts, maybe that the dependence the actual dependencies are because the bubble on the left actually uses the data that is used by the bottom bubble on the left, and the bubble on the right by the bottom bubble on the right. The idea we would like to do is be able to explode those outer level bubbles and build the proper dependencies between the inner ones. Okay? This is the type of things I believe are not well supported today in nesting and would be important to support. Let me go to another topic, which is task loops. Task loops today don't support dependencies, and we think it would be a very, very interesting thing to have dependencies within tasks for corresponding to the same task loop. Dependencies between tasks of the task loop and external tasks, previous or ulterior tasks. and combining these two things. So this is another of the features that I would like to see work happening, because I believe it's an important thing in order to really enable the instantiation of a lot of work. Third topic about OpenMP OMS type of activities, interoperability with MPI. So the task-based model, the idea is that you can execute out of order tasks for a computation is nice, but when you encapsulate an MPI call, you end up being able to execute out of order computations with respect to communications, but also communications between themselves. And I think this is a very, very important type of functionality. And actually, if you think what we have done in MPI, what we do, when you look at our programs in MPI, well, we are working on parallelism, but in reality, we have a lot of internal sequential kind of behavior within the MPI process. We use very few communicators, which is a shared context, potential shared context between threads. We use we rely a lot on the ordering characteristics of MPI, and there's a lot of that can be kind of extended, can be overlapped, and we can achieve a lot of much higher overlap than what we are getting today in terms of between communication and computation. And we get it just for free, keeping the current syntactical structure of our programs, just properly annotating tasks. And the final topic about the things that I believe in OpenMP are important is malleability. Being able to really dynamically adapt the amount of resources that the process is using a long time. And actually, if you think of Andal's law, the way I see it is a nightmare for people who has MPI programs and now wants to go to do OpenMP. What it tells you is you have spent 20 years doing your MPI program parallelizing 99% of it, and you have to go now and use OpenMP, spend again 20 years to parallelize 99% at the OpenMP level. The idea is sometimes one kind of cannot do it, gets tired, and then we still have a lot of sequential parts in our programs that when you go at very large scale, very large number of threads, they still are important. One alternative is to really have this dynamic capability of shifting cores between applications, between processes in one node, that lets you use, here in this example, you can use while one process is in the blue part, which is serial, other processes which are in the red part could actually increase their number of threads. The result of these things would be that actually with less effort, with very little effort, and actually the productive way that we think is if you have imbalance in your application, use hybrid, only parallelize with OpenMP those regions that expose imbalance at the MPI level. And this type of technologies of dynamically shifting cores between processes will help you actually get to the point of very good efficiency. So what I'm going to say is this was all about APIs, about the API for the programmer. What this decoupling gives you is the possibility to do again all that architects were doing in hardware. You can do it today, now in software. You can work on the runtime, and you can work on scheduling things. You can work on managing the movement of data between registers and between memories. You can work on implementing resiliency stuff. There's a lot of flexibility, as well as for architects to do kind of re-engineer the low-level part of the machine in a way that actually merges more with the runtime, in a way that, because this will not be visible to the programmer, and this gives flexibility for both communities to work again together, and maybe end up with something that instead of being separated in the two layers is something that is again a single runtime-aware type of architecture, or as an integrated development. The good thing is applications will remain the same. It's a little, I think, goes a little bit in the direction that you mentioned. Can this be done with is OMS? The idea is generic. You can do the same idea with other languages. You can do the same idea with Java. We can do the same idea with Python. And we have this type of work where you, in Python itself, you have functions there that you can annotate with decorators. In these decorators, you specify the directionality of the arguments. And you may, as you have here, you have an example where actually you can specify resources, you can specify some other constraints, but the result of this, and it's only annotating these functions, the result of this is that the execution of the main program results in the automatic generation of a task graph, which can then be scheduled by the runtime to other nodes, other cores in the same node, other nodes in the same machine, other machines on the cloud. Okay, it can be done in a very dynamic, very elastic way. So we believe that the philosophy that, and all of that comes from, I think, from these annotations and annotation suite. In the same annotation give you information to exploit concurrency and exploit locality. I'll shift to the other topic, which is tools. And I've been showing plots of tools during the programming model part, because really you really need to understand the details of what you are doing. Why do we do simulations today? Why we look at this, try to detect the last photon of coming from the stars? We look at the detail because it's the detail what determines the macroscopic behaviors. And the idea is, in order to understand and to really obtain the full performance of machines, we need to understand, I think we need to have the mechanisms to understand the details, to be able to find needles in haystacks. And I like to use this, have you ever seen the rain or have you seen the noise? This is an example. This is an example we got from cooperation with NCAR. It's something, you have here a timeline of 1,000 processors. And the different colors represent MPI calls. At the beginning, there are point-to-point calls. At the end, there are collective calls. And this is the timeline, the 1,000 processes and time. Just the colors, and this is like the stars. This is looking at the reality of what happened in a given execution from the point of view of the MPI calls. This is looking at the same stars, looking with a filter that tells you how long are the computations. They are longer at the beginning, darker color, not so long at the end. And by the way, there are intermixed around there are regions which are relatively long, dark. So the idea is, what we need is to have mechanisms in the tools to be able to navigate between this time-space dimension to a dimensions which is, these are histograms. You have also rows, one row per process, but histograms that tell you how long is the computation, and go back from the histograms to the timelines and say, these are the regions where you had longer computations than what you would expect. These are the regions where you have noise. You can kind of detect, and the point here, the essential message is, it's an example that noise is, we think it's a very small part of our system's behavior, but in reality, detecting it and seeing what's the structure is something which is important. And the idea is being able to find finer and finer details. And by the way, noise is not the last problem, the last question. There's always going to be a next question. And what the powerful analysis tools will give you is the ability to try and answer those questions without requiring, with the available data, without requiring huge amounts of new experiments for every new function. We have to be able to squeeze the data that we have in order to get those results. In reality, I mean, there will always be questions that we won't be able to answer with the data that we have. But it would be nice to be able to do 3, 4, 5 iterations of a kind of hypothesis validation process before requiring this new additional data. So this is one of the features of the tools that I think is important, and it's important for the very fine-grained detail. But if you do it manually, it's kind of a little bit tiring. Then the thing is, how can we do, and I like to look at the performance tool as for me, is the data killer, big data type of application. Is we don't use actually that much machines to understand data that comes from itself. We use them to understand data coming from the stars, but we don't. There's this saying which is the shoemaker's son going barefoot. Okay. Well, a little bit like that. And I think we have, with the ability to generate a lot of data, introspective data about the behavior of our applications, and we don't apply that many analytics. So we have been trying to look a lot at clustering type of techniques. What if you determine, if you group only you look at the computations and you put them, instead of in the timeline space, you put them in these scatter plots, which represents on the vertical axis instructions, so computational cost, complexity of the actual user level computation, IPC in the horizontal axis, and it comes out that they cluster relatively well. You can propagate that to the time dimension, and it gives you information about the structure. And I think structure is a very important fundamental thing. And if you look at how these points move in an iteration space, for example, when you increase the core count, IPC may shift a little bit, or the computational cost may reduce. This is this plot on the bottom right is kind of a strong scaling, and you expect the centroids of those clusters to go down because you are increasing the number of core counts. You would like the IPC not to get worse or better, but this may happen or may not happen. In the example, there are some of these points that don't move at all, meaning that they are actually replicating code. So what I'm trying to say is there's a real need for getting a lot of, or applying a lot of analytics and leverage analytics from many, many different areas of sciences. I mean, you can use machine learning now, but you can use, we have been using here traditional clustering algorithms adapted to the special characteristics of the performance data. We've been using something I think is very nice, is life sciences algorithms. You have sequence alignment. If you think of every process, every thread as one DNA sequence, if your programs are SPMD or BSP type of programs, you would actually expect them to go through the same sequence of phases. So you can actually use this type of sequence alignment codes from life science people to do analysis of the behavior of the machine itself. This is, I think, it's a very interesting type of thing. And what we have to have is an open mentality that gives us the possibility to really leverage technologies from any other area. The thing on the right is these tracking techniques that you'll have a lot of tracking demos on the exhibits about tracking cars or tracking people. Why don't you track clusters in this case, or points which represents performance behavior of given code regions? Other thing that I think is important is having the ability of doing what-if analysis. What if my machine was a little bit faster in terms of communication or a little bit slower? What would be the performance if I had only 10 megabytes per second of communication bandwidth? Even more, what would be if I detect with the clustering analysis that there are regions that are imbalanced? What would be if I manage to balance those regions? Will I get a full performance, a full impact of a full gain on my application or not? Having indications of how these things will evolve is something that for all the porting activities we consider would be very good. So starting a porting activity without some expectations of how much you can really gain or not is risky, is dangerous. But till now, everything was lots of data, lots of colors, lots of plots. Still something that not many people may be willing. I will enjoy doing that, but not many people will enjoy looking at those. The question is, as with big data things, can we summarize performance in few numbers? And this is the kind of very simple models that we look at. Just how do you describe parallel efficiency with 3 numbers? And the numbers is not profile thing. MPI, or saying the time in MPI, MPI is often blamed of many things which is not responsible for. Okay, so it's like a gas, fills whatever space you give it. The important thing is, do you have load balance? Do you have serialization effects? And can you quantify how much is really the impact of transfer? And this is what we try to characterize with these models. Very simple things, very simple concept, but constitute an abstract framework with which you can actually discuss with the people, with the users of applications. It's easy to compute, very easy to compute. You need probably one thing that everybody would like. I don't know how much would you like to pay, for example, for a machine with infinite bandwidth and 0 latency. I don't know how much would you be ready. I think everybody should have one of those, and actually determine and see how much would your application gain if you achieve that. So with that I cannot give you in terms of machine, we can do with a simulation, and this gives us insight into the actual dependencies of the application, and this lets us separate these terms of serialization and transfer. So let me show some examples. What this gives, and I think is important of the models, is that gives kind of a common ground by which you can describe and compare and reason between users of application and applications of many different areas. We have this project, this POP project, where we are actually analyzing the different applications and reporting these three simple numbers: performance, load balance, serialization, and transfer on one side. Well, maybe also a little bit the left part of that tree, which is about how do you characterize the computational performance part, and whether it has to do with the IPC or has to do with the efficiency, energy, right? So what are or the amount of instructions? What are the factors that determine performance in a simple model? And I think this is important to have communities really talk the same language, which is not the application language, the scientific domain language, but just the behavioral domain language of the application. So this is what I think is important for the applications analysis, for the users. Let's go back to the revolution. How does this, all this, what does this implies in terms of the revolution? And what is a revolution? Okay, and from my point of view, a revolution is something that, I mean, may have some transitory phases where maybe shaky or more or less shaky, but the revolution is something where, is something that kind of means or represents a change in the way of thinking before the revolution and the way of thinking after the revolution, okay? And how could I summarize the type of things that, what I've been describing is technologies, nice technologies, I've enjoyed working on those, but what kind of summarize the vision of how the revolution of the multi-programming or the multi-core era, let's say, of the current exascale type of target, how can it be characterized? And what I think is, what describes the behavior before the revolution is that we lived in an age dominated by latency. We were dominated by how fast is our memory, how can we do caches to get our data faster, how fast can I do my interconnect to do my MPI with less latency. And we had this type of programming where I say, I want, it's like kids, okay? I want this, and I want this. I want to load this data, period. Until I don't get it, I don't do anything else. So this is a mentality also thing for the user, for the program developer. We have to go to another way of thinking, which is the throughput age, is where I have this possibility of saying, I want this, and I want that, and I want that, and the other thing. And when one of them comes, I can ask for another one. But as long as they keep coming, I get I'm happy. Otherwise, I'm just crying when my control flow stalls. Yeah, I have to cry. Okay, so I think we have to shift to this other way of mentality, or seeing our machines, or seeing the way we write our programs, and which has a message which is, actually, in this environment, performance will not be dominated by the latency itself. Performance will be just a matter of how many resources we throw at one thing, okay? And I think this is an important change in mentality, which does not, from our point of view, require a tremendous change in the programming models. What we have proposed in terms of the STARS model is that revolutionary? Externally, may not be. From my point of view, it is, because it has to do with this change in mentality of not being dominated by latency. In a sense, and I think we have to forget exactly about the hardware. It will be there. People, architects will do it. For sure, it will be there. Okay, we have to think more on this kind of ordering things, on this kind of dependencies, on these potentials, rather than specific how-tos. We have if we have the proper interfaces, which may be related with what I presented or not, but the idea is, if we're able to develop these proper interfaces and we are able to rely on the underlying system, I think we'll be able to achieve it. And I know it's difficult. I know we are sometimes afraid of many things, of losing control. We are sometimes very proud of what we do and saying, I can do it better. And probably some people can do better but probably not. And I think that there's a lot of potential to gain. We have a lot of cases where you can say, okay, overhead of those techniques. But what you gain by getting proper ordering of things is far more important than what you lose by some overhead of some of those. So we have to learn about the details, which are the techniques which are appropriate, but I think that that's important. Of course, all of this will be steered or driven or done under a detailed capabilities, analysis capabilities, because it's a very, very complex, very fast space, and we have to be able to navigate it. We have to avoid flying blind in this situation. We may be very close to a solution and not detect it, or we may be very happy and being actually very far from the optimal thing. And it requires education, a re-education effort. And sometimes I get the feeling that it's easier to shape minds than to reshape minds. Okay? Sometimes we are very obsessed with a given way of looking at things, and it's difficult to change to a way of, a more open, I would say, way of looking at things. So from my point of view, this would be the actual real message. The actual real message is we've been enjoying working on technologies and doing this programming model or the other, or this tool or the other. But in reality, what will determine the change in mentality is the change in the revolution is the change in the mentality, in the mindset of programmers. In changing from looking at the world and seeing the world with a latency-dominated vision or attitude, to looking at it with a throughput-oriented vision or attitude. I think it can be achieved. I think technologies will go in the direction of supporting these things, and it's something that depends on you, on us, on all of us, to really change the way we face the future. Very large-scale computing, but it's to exascale and before. It's a very generic, very general type of consideration. Thank you very much.
Thank you, Jesus. We have time for a couple of questions if people would like to come to some of the numbered microphones. While people are gathering at the microphones, I wanted to ask you one question. Returning to your theme about moving away from being so explicit about programming exactly what moves where and when, forever it seemed the holy grail is to get back closer to the math than the expression of the data. And do you think we'll ever get to the point we'll be able to express our programs as mathematical equations rather than directions to a machine?
Well, and probably has to do with DSLs, right? And how high level these DSLs are going to be. And the way I do really see there's room for DSLs. Our approach till now, what we've presented here, was a kind of programming model, which is a general purpose, more traditional type of programming model. But in the same way that it allows for applications to be thinner, it allows for DSLs on top of it, and that's what I think, to be on top of it, to be thinner. And I do believe that there is a lot of interest and a lot of potential in going into that direction, as long as we have this kind of hierarchical implementation. Yes.
Great. I think we have a question at microphone 2.
So I actually have a question, two questions. One is about your, well, both of them are about your task-based models. The first question is, how would you address nested level of thread parallelism? So sometimes your bubbles that you have shown themselves use threads, and those threads don't play nicely with your other threads in your task-based model. And second is, how do you address debugging? If something goes wrong in your task-based model, it can be very difficult to debug because it's not your own program or software, it's now this runtime that is somewhat obscure. Thank you.
Okay, thank you. Thank you. So the first question is, how do I address threads? I don't, right? I think threads are maybe a bit tough. Threads are a mistake. To present threads to a programmer is a mistake.
Okay.
I think threads are resources. It's a resource, and what we specify is computations, is tasks. Whether they are, how they are mapped to the specific hardware, to the different threads, I think is really not what the programmer should be specifying. Okay, that's what I think. The other thing is debugging. we have been working, cooperating, this has been done with cooperation with Stuttgart people. They have been working on debugging for this task-based model where you actually represent the tasks themselves and which of them have been actually, what's the actual status of the task execution engine, let's say, on one side, which actually has the possibility of presenting the evolution of your computations at this level, but has also the possibility of executing, of going into the inner level of the classical standard debugger. So I think really there's the possibility of doing that, but certainly requires a little bit more of well, again, the change in mentality. But I don't see a major problem. The good thing with the task-based model is, and this is not there in the other parallels, that the task-based model is the original. The origin is sequential. And the fact that the original program is sequential means that the order is defined. And you try to then change whatever you can, but the actual order, there's always a fallback position. Order is defined. The problem with parallel programming is when things are very parallel, it's very nice, it's very easy. The problem is when you start having to reintroduce order. Okay? So from this point of view, I do think that there is a lot of potential in terms of making the debugging of these systems easier.
Why don't we go over to microphone number 3 right now?
So I guess to complete this revolution at some point, would you expect all applications to be rewritten with some kind of tasking, or is there a better way?
I do think so, and I don't know whether it was clear. I don't know, maybe didn't get the message properly, but I think it will be. I would say it will happen, and it is not difficult. It's not changing. It can be done incrementally. You don't need to do it for everything. You can take your current MPI plus OpenMP, right? And you can do that in a relatively easy and relatively incremental way. That's my personal feeling, as long as you have this change of your mentality. So it will be incremental, but it will be. That's my view.
For a final question, we'll go over to microphone number 1.
So back in the olden days, 20, 25 years ago, when you got a new machine, you often had to change your algorithm, explicit method to implicit, direct solver to iterative solver. Has that changed with the new machines?
So, but that's an algorithmic thing that may partially change depending on but it's not something that depends on very detailed architectural things. It's a very high level, very algorithmical level. It may happen. I don't know. You may use, instead of using a real finite element code, you may train a neural net to approximate the function. Okay, so there are a lot of these things that will happen, will continue. So will continue happening, right? But this has to do more with the algorithms, with the computational complexity and communication avoiding algorithms, with the characteristics of the algorithms than with the machines themselves. There will be some relationship, yes, of course. It is the total dependence that sometimes we think we have, I don't think.
Thank you. Unfortunately, we've run out of time for questions. Will you please join me in thanking Jesus for his thoughtful comments and congratulating him on his Ken Kennedy Award.